Hello again. Today we have homework. This homework has 5 questions, and each of these questions have some different code fragments that we need to find the time complexities of each one. Let's start with the first one. To analyze the time complexity of the given function, partial sum of squares, let's break it down. The function iterates over each element of the array R, as you can see here. For each element, it checks if it's negative in here, if I is smaller than 0. If the element is negative, it squares it and adds it to the result in here. Let's analyze each part of this question. The loop iterates over each element of the array R once. Therefore, the loop contributes O parenthesis n to the time complexity, where n is the size of the array. Checking if each element is negative is a constant time operation denoted as O parenthesis 1 because it involves only a single comparison. Squaring the number here and adding it to result is also a constant time operation, O parenthesis 1. Since each operation within the loop is constant time, and the loop itself iterates through each element of the array once, the overall time complexity of the function is O parenthesis n, where n is the size of the array. So the time complexity of the given function, partial sum of squares, is O parenthesis n. Let's continue with the second question. What are the time complexities of the following code fragments? Start with the first one. This loop iterates n squared times where k++ is executed in each iteration. Therefore, the time complexity is O n to the power of 2. Let's continue with the second one. This loop iterates n to the power of 2 divided by 40 times. Since it's a constant function of n squared, it doesn't change the overall time complexity, which remains O parenthesis n squared. Let's continue with the third one in here. This loop iterates n times, just n times. This time complexity is O parenthesis n. The fourth one, this loop iterates approximately n to the power of 2 divided by 6 times, considering n times n divided by 3 to be the range here, as you see. Therefore, the time complexity is O parenthesis n squared. In the fifth one, this loop iterates a fixed number of times. It's, I think, yeah, it's 1 billion times, irrespective of n. Therefore, the time complexity is O parenthesis 1. It's just that. The sixth one, this loop doubles I in each iteration until it reaches n. The number of iterations needed to reach n from 1 by doubling is logarithm n base 2. Therefore, the time complexity is O logarithm n. And this one, this loop iterates a constant number of times logarithm n divided by logarithm 4, which simplifies to a constant. Therefore, the time complexity is 1. In this one, things get a little bit complicated here. This nested loop runs n divided by 100 times m divided by 4 times. As we can see here, n divided by 100 times m divided by 4 times. Therefore, the time complexity is O parentheses n and m. And the last one of this question, the outer loop runs logarithm n times base 5, as you can see here, and the inner loop runs m divided by 2 times. Therefore, the total time complexity is O parentheses m times logarithm n, as the inner loop runs half m times. Yeah, this question is done. Let's continue with the third one. The time complexity. What is the time complexity of the following power function? The time complexity of the provided recursive power function can be analyzed based on the number of recursive calls it makes. Let's break it down. In each recursive call, the value of n is halved until it reaches 0 or 1. 0 or 1. Approximately, this results in approximately all logarithm n recursive calls, because each time n is halved, at each level of recursion, there are constant time operations, multiplications, divisions, and modulo operations. These operations have a time complexity of O parentheses 1. Therefore, the overall time complexity of the recursive power function is O parentheses logarithm n. Let's continue to the fourth question today. What is the time complexity of the following Fibonacci function? Here we have a Fibonacci function. The time complexity of the given function is exponential, specifically O parentheses n 2 to the power of n. This is because each call to recursive fib generates 2 more calls, leading to a binary tree structure of function calls. Each level of the tree branches into 2 recursive calls until it reaches the base cases and is smaller or equal to 2, which terminate the recursion. The number of function calls at each level of the tree roughly doubles with each increase in n, leading to an exponential increase in the number of function calls and thus exponential time complexity. This was the following Fibonacci question. Again, it is exponential and specifically O parentheses 2 n to the power of 2. Yeah, let's continue with the last part of this homework. Faster computer or algorithm. Suppose we have a fast computer that is 10 times faster than a slow computer. We have a problem with two different solutions. Fast algorithm takes O parentheses n time. Slow algorithm takes O parentheses n squared time. Okay, which is faster? Slow algorithm running on fast computer, fast algorithm running on slow computer. To determine which option is faster, we need to consider O parentheses n squared times 1 divided by 10, since the computer, fast computer, is 10 times faster. We divide it by 10, and simplifying it, it becomes slow algorithm to run. It becomes O parentheses square of n divided by 10. The fast algorithm on slow computer, in the other hand, the time complexity is O(n) times 10, since the computer is 10 times slower. Simplifying it, it just remains O(n). Comparing to the two, O(n), the fast algorithm, is significantly faster than O(n squared divided by 10. Therefore, the fast algorithm running on the slow computer is faster. The reason for this is that the time complexity difference between O(n) and O(n squared outweighs the effect of the computer speed difference. Even though the slow computer is slower, the improvement gained from using a more efficient algorithm is greater for everyone. So the difference between the hardware won't affect us so much. Yes, this was the video. I hope you like it, and if you have any questions,